Hi everyone, this is Mr. Lee. In this video, we are going to go over the work energy theorem. All right, let's begin. So just to start off, the idea of work. So work is a term that we use a lot in our day-to-day lives. Like I have homework, or I got to go to work, or I'm doing work. However, for us here in the physics world, work has a very specific definition, and we're gonna go over that. So keep that in mind as we are going through these ideas. So the first thing I want to do is I want to start off with a classic problem that we've been doing, and that classic problem is we have a ball. This ball is held up at a height of h, right? And there's an Earth here, okay, and this ball has a mass of m, and we'll just say that the initial velocity is 0. All right, and this ball falls to the Earth, and let's just make it simple for us. We'll say it's like right as it's touching the Earth. So right as it's touching the Earth, there is a final velocity. The ball still has mass, but here's the important thing: the height is going to be 0, right? And the Earth still exists there. Okay. So the reason why I want to start off with this is in class I've been hinting at the idea that this idea of the Earth is very important, right? Label that Earth because when it matters, it will matter a lot. So the question is, we know that on the left-hand side, the initial side, the system, okay, has gravitational potential energy. And we know that because we have an object, it's under the influence of the gravitational field and is at a height above. And we say that the energy gets transferred from the field into the motion, which is 1/2 mv squared. So the idea of the work energy theorem is what gave the field the energy in the first place. Okay, so where did this energy come from in the first place? What gave the field energy? So let's try to answer that. I'm just going to scoot over here so I can write some notes on the side. Let's first go over the idea of like a couple things that you need to be looking for as you're doing practice problems. So the system. For this unit, the system is the most important thing that we can be looking out for. We've discovered the system before when we did the at-will machines. If you remember, for the at-will machines, we did the dotted lines around the system. Okay, in the system, when you do that method, it helps you identify what our focus is on. But for the work energy theorem, the important thing about the system is that energy can enter/leave the system. So the conservation of energy says that the energy that we have initial has to be the energy that we have final. Okay, that's what the conservation of energy says. Now let's add to that definition. So this is the conservation of energy, right? Our energy initial has to equal to the energy final. But this is only true if we have a closed system. So the idea of the closed system is that everything that we have in the drawing is our system. So for example, our beginning problem, our system, would be the ball and the Earth. So we have a ball-Earth system. So what that tells us is that the energy initial, or UG, will still be in the system with KE. So just to give you an idea, the ball will gain kinetic energy. And where did that kinetic energy come from? Well, it came from the Earth's gravitational field. Okay, so that's what we call a closed system. Energy can't enter, energy can't leave the system. So now we have the idea of work. Work is the only way where we can add energy to the system. So let's have that definition down. So work is adding, or I guess subtracting, right? We're taking away energy from the system. So if we take a look at our original problem where we have a ball above the Earth or the ground, okay, and we release it. In that problem, everything that is necessary for the system is already there, right? We have the gravitational potential energy, UG, and that UG turns into KE. However, watch what happens when we redefine the system, like so. Okay, so let's do it. Right underneath of it, we'll say the system is just the ball. Okay, so when we say the system is just the ball, that means we're not considering the Earth to be a part of the system. So how we will draw it is still the same. So we have a ball up here, okay, and we say the ball has a mass m, it still has a v initial of 0, and there's still a height h, and there's still the Earth here, okay, g. However, what we're going to do now is just like what we did with the forces unit and the at-will machine problems, we're going to draw a dotted line around the system. And just as a reminder, the system is just the ball, not the ball Earth. So I'm going to draw it like this, okay? Meaning that whatever is inside the dotted line is what we can say has energy, okay? Now, when that ball falls, let's say it's right there, okay, the system is still the ball, so I'm going to do my best to not include the Earth here in my drawing. Okay, G, our height is still 0, but now we are moving, right? V equals V final, and this is still the mass M. All right, so the reason why I try to put such a big emphasis on drawing and labeling the problems is because, once again, the drawings give us the formulas. So let's take a look at this idea of how defining the system changes the formula itself. So normally we would say that there's UG, right? And we know that UG is MGH. However, we can't say this anymore because the system does not contain the Earth. Notice how the Earth is down here, and this dotted line does not encapsulate the Earth, meaning it doesn't look like this, right? We didn't draw a dotted line that looks like this, okay? So if I were to draw a dotted line like this, we are now including the Earth, but we're not doing that. We're just including the ball. So there is no G to give us the field, which gives us the gravitational potential energy. So there is no gravitational potential energy here, okay? But we do know that at the end, there is still kinetic energy because the ball is moving, right? This we know to be true. So the question is, what gave the ball kinetic energy? Okay, now in your head you might be thinking, well, I know, it's the Earth, right? Because that's what we've been doing, Mr. Lee. We've been saying that the gravitational field gave the ball energy, and you are very correct. But because we didn't include the ball within the system, now what we can say is that the Earth or the field did work. So let's write that down. So the Earth or the G does work on the system. Okay, that's just one of those things where the problem doesn't really change. It's just how we look at the problem. That's the big thing that changes. Okay, so we can say that the work done by gravity will equal to the kinetic energy. Okay, so there is a general formula for work. But before I do that, what I'm going to do in my initial drawing, some of you have been doing a good job of doing this, and that's drawing a free body diagram. All right, so we have to bring that back. So if we take a look at the ball, I'm just going to do a quick free body diagram right there. We have FG. Okay, so the reason why this free body diagram is important is because the formula for work cares about the direction of the force. So the formula for work, I'll do it over here, is force, okay, times, I do times with a dot, this is what we call a dot product, times delta x. Okay, so when we multiply using a dot or a dot product, this tells us how aligned are your vectors. Okay, now mathematically, what this tells us is that we're looking at the cosine vector components. Okay, how aligned are your vectors? So we'll go a little bit more into that later, but let's just finish up the formula. Okay, so what this will tell us is that the work done by the gravitational field gives us the kinetic energy. So for this problem, we say the force times delta x, and because it's the force of gravity that's doing the external force, we can replace that with Fg. And you know what? It's a good habit. let's take it one step further. mg times delta x equals 1/2 mv squared. Now this is really cool because if you take a close look at this formula, this looks almost identical to the gravitational potential energy formula, which is mgh equals 1/2 mv squared. And I'm here to tell you that it's the exact same formula, except up here we use delta x to tell us the change in height, but the gravitational potential energy, it has height already in it. Okay, so the work done by the field gives us the kinetic energy. So this is the work done by the field gives us the kinetic energy. Okay, and this is true if and only if we do not include the Earth within our system. So let's go over here to take a deeper dive at how aligned are your vectors and why that's cosine of theta. So in our original problem, we had the ball and we had f of g pointing down. Okay, so that's where the f comes in. So what the delta x tells us is what is the displacement of the object as it goes from there to down here. What is the direction of that delta x? So the direction of the delta x would be down as well. So if I were to line up my fg and my delta x, okay, so this is fg, and here's my delta x right there, right? Notice that the angle between my two vectors is 0, meaning if I do a cosine of 0, that gives us 1. So it tells us, what this tells us is that 100% of the force lines up with the displacement. Okay. Now, in terms of work energy, okay, because dot product is something that we'll see in other parts of the course, and dot product is just a way of describing things in nature. Okay, and it describes how aligned it is. So what this statement tells us in terms of work energy is that 100% of the force results in a change of energy. Because remember, work is adding energy to the system or taking away energy from the system. Okay, so let's do something where your where your forces and your displacements are not lined up. Okay, so let's do this as a different example. So let's say we have an object, right, a box, and we're pulling this box along the floor with a rope. So we'll call this T. Okay. So step one, always draw your free body diagram. So we have FG, and then we have FN this way. All right. So there's a free body diagram, and we're going to include FF here, force of friction. Okay. So that's going to tell us a lot later on. So if we take a look at this, and I'm going to do this in a different color, okay, and I suggest that you do this as well. We know, I'm telling you, that the object is moving to the right. How do we know it's moving to the right? Well, the force of friction is pointing to the left, okay, and that's going to slow us down. And so therefore, if it's moving to the right, our displacement of the object will also be to the right. So if we take a look at each one of these forces, okay, let's take a look at the ones that do not line up, do not align. So we have f of n going up, but our displacement is to the right. So if I were to ask you, what is that angle in between the two, you would tell me, well, it's 90 degrees, Mr. Lee. And that's very good. So if we take a look at the formula, work is equal to F dot delta x, or we could rewrite this as F delta x cosine of theta. Okay, cosine of 90 gives us 0. So I'm going to write that down. So what this tells us is that our normal force does 0 joules of work, meaning that this surface, okay, so surface is not causing a change of energy. So let's think about it. What would be that change of energy? Well, because the object is moving, we can say the change of energy would be kinetic energy. So what this is telling us is that the surface or the normal force does not make the object move. All right? So let's think about the other one, Fg. So we have Fg, I'll move this to the side. We have Fg going down, okay? And the object is still moving to the right. And so here, this is still 90 degrees, and we don't have to go through the entire process here. I'm just going to skip right to the end because cosine of 90 gives us 0, so 0 joules. So what this tells us is if the object is moving to the right, the force of gravity is not causing the kinetic energy, right? Because it's not. It's not going downwards. It's going to the right. So the force of gravity, which is pointing down, can't cause it to go to the right. Okay. Now let's take a look at that tension force. So we had an angle tension force, and this is where the dot product or how aligned something is matters. So what I'm going to do is I'm going to bring back the components. So if this is my tension force T, we can say that this here is Tx, and this here is Ty. And the object is still moving in the horizontal axis. So taking a look at this, okay, we can say that Tx and delta x, they are on the same axes. So W is equal to F dot product delta x. So this will tell us that what is the force that's actually causing this change in energy, right? So we can say that it's T cosine of theta, right? So if this is your angle, Tx, okay, is the adjacent side. So T cosine theta times delta x will result in the work. So if you're looking for like an intermediate step, I would write it like this: WTx, which is the force, times delta x, okay? And this leads to this formula here. So you can see, if you're looking at the components, that cosine of theta, okay, there it is. It all lines up. And the cool thing about it is it really depends on the situation here, but that cosine theta just tells us the direction or the component here, okay? But in terms of math, the thing that we are looking for is how lined up are the forces with the actual motion, okay? So this tells us that the Tx causes, okay, so the rope pulling to the right causes a change in kinetic energy, right? So that Tx is actually making it move. Ty does not cause a change in kinetic energy. And keep in mind, the definition of work is the change in energy. Cool? All right. So that leads us to the last force, the force of friction. All right. So we had total of 4 forces. This last one, we have an object. Oops. Let's just go straight to the force. So we have the force of friction, and the force of friction is pointing to the left. However, this object is moving to the right. So the question is, okay, what is this angle right there? And this will be 180 degrees. So going through the work, we would say F dot product delta x. So it'll be force of friction times delta x times the cosine of 180. So cosine of 180, this gives us -1. So what this tells us is pretty cool. We have a negative value here, right? All of this will turn out to be negative ff times delta x. So this is an important idea. So what this tells us is that the force of friction takes away kinetic energy. Okay? And in terms of like real life or everyday language, we say the force of friction slows the object down, okay? Because that's a decrease in kinetic energy. Isn't that cool? So here are a couple of rules of thumb. All right, let's just go over the definition one more time. Okay, work is the change in energy. So whether it be change in potential energy or kinetic energy, all right, work is a change of energy. The formula is force times delta x. And remember that delta x is a velocity, that delta x is how much it actually moves, okay, the actual displacement of the object. And negative work is takes away the kind of energy. So it can either take away potential energy or it can take away kinetic energy. And here's a good rule of thumb. slow down forces or forces opposing always has negative energy. Okay? So this negative energy, okay, this is one of the fundamental rules of our universe. What we call this negative energy, or the energy generated by friction, we call it heat. And heat is a very important idea. So we say that the universe will eventually die when there is no usable energy. So usable energy can be in the forms of like potential energy or like kinetic energy, right? But if we have heat, heat is unusable energy, meaning that the heat that we generate as human beings or our appliances, we can never ever capture it again to use that heat. It's gone forever. And that gone forever idea is what we call the heat death of the universe. And it's one of those fundamental laws that tells us that eventually the universe will run out of usable energy. And it's all because it's just in the form of heat. And this is what we call entropy. Wow. All right. So, yeah, we have that. And that'll be it. I'll see you all next time. Bye bye.